I like to use x's for the singularities. I don't know, it's just what I do. So if you think about different points finding the solution around, here's an easy one. If I center my solution at 3, right, if I choose x naught equals to 3, if I looked at y equals to c naught plus c1 times x minus 3 plus c2 times x minus 3 squared plus dot dot dot, this would solve star star. Let's call this thing, yeah, star star. This would solve star star where? You think about the disk growing out of here, and the first thing it hits is that, right? So we're going to get 2 to what? This distance is what? This is 1, right? So minus 1 plus 1, so 2 to 4. I'm not sure if 2 is included or not included. I have to, you know, that's again, that's, you know, whatever. Now let's see, what would be a more exciting point to think about? How about minus 1? Where would that, if we looked at that solution, where are we guaranteed for that to work? Oh, I think you're right, actually. Yeah, I think you got it, because it hits 0 first, doesn't it? Yeah. You're right. Yep. Very good. Let's see here. Let me see if I can figure one that's a little bit, I'm trying to find one that's, the really fun ones are complex, admittedly. But again, I'm trying to behave and not do that. Let's see here. How about if we center it at x plus, yeah, no, 3/2. You know, center of 3/2, minus 3/2 rather. 3/2 is easy. If you look at 3/2, that would work like this, right? It bumps up against the 2 first, clearly. But the thing about minus 3/2 is it's not immediately obvious to me whether it hits these imaginary singularities or the 0 singularity first. Right? So how would you figure out which one actually limits your domain? It's pretty simple. Relatively simple. What do you do? I mean, there's really just one question, which one's closer, right? So I have to calculate the distance from minus 3/2 to the origin. That I can do, 3/2. Right? And also this distance. So what's the distance between this distance here? Let's see here. So there's a little triangle, right? You can draw the height of the triangles too. And what's the base of the triangle? 1/2, right? So I do 2 squared plus 1/2 quantity squared, Pythagorean theorem, right? So that's the square root of, what is that? 4 plus 1/4. It's kind of pretty. But it's kind of useless too. I want to compare it to 3/2, yeah? I guess I can convert that to square root of 17 over 2, yeah? 16/4 plus 1/4 is 17/4. And then the question, right, just becomes, which is bigger, the square root of 17 or 3? Well, the square root of 17 is bigger than the square root of 16. It's larger than 4. So apparently, the thing that's closest singularity is then what? It's like this is the winner, right? The origin wins. It's closer than the complex singularity still. And so this would have, this works on 3 halves, well, minus 3 halves, minus 3 halves, minus 3 halves, plus 3 halves, you know. In other words, minus 3 to 0. And if my picture was better, right, you could tell that this point was closer to that than to that. It's not actually the case, right? My picture's not to scale. In fact, my singularity on my picture is closer than the origin, right? So pictures can be deceiving. That's why we have to use analytic geometry. Constructive geometry should have died with Hilbert. Unfortunately, we still teach it. Sorry. You like constructive geometry? You're so old-fashioned, Luke. What's that? You take that as a compliment? Yes, I thought maybe. That's fine. All right. So, method of Frobenius then. We assume that we have a regular singular point. All right. And what does it look like? What's the method of Frobenius? How does it work? Basically, you assume that the solution looks like W of Rx, which is going to be equal to x to the r times the sum n equals 0 to infinity a sub n x to the n, which you could rewrite as the sum n equals 0 to infinity of a sub n x to the n plus r. That's the start of it. We assume that the solution at a regular singular point can be written as this so-called Frobenius solution. Do you guys have any? So basically what we're going to do next time is we're going to take this and we're going to plug it in to that under the assumption that we're at a regular singular point, and we're going to work it out blow by glorious blow. And it will take me a solid hour at least to get through it. Now, do you have anything? I mean, just look at it. The thing I always thought when I first look at this is like, what difference does it make? You know? I didn't think that. That's a saying that's been more recently ingrained in my mind. But you know, isn't this just a power series? Like, so why is this different? Thing is, no, this is not a power series, generally speaking, because R is not necessarily in the natural numbers. In fact, we're going to find R could be irrational, like it could be a half, it could be a third. R could even be complex. So this is not a sum of power functions. It ends up being a sum of, well, it is a sum of non-integer power functions. It's much broader class of functions as models. And in fact, this method of Frobenius is used to define many of the special functions which are important to mathematical physics. That's the last section in this chapter. We may or may not get to it, you know. But anyway, so you can turn it off, Luke, if you want. That's all I got for today, talking wise.